Ithaca, New York, then infamous for its cold, harsh, bitter, desolate, barren, depressing, and otherwise tolerable winters, where heat is carelessly leaked out of campus dorms. An insurmountable amount of energy is wasted every single moment through various flaws of building construction and in careless human behavior. One small group appears the only thing standing in the way of climactic destruction.
Global warming has become one of the most pressing issues of our time. There are many actions people can take to mitigate this problem, but some of these are not realized by many people. One of these issues is heat loss in buildings due to poor insulation. In this video, we did a case study on heat loss through windows at 2 dorms at Cornell. These 2 dorms, Mary Donlan Hall and George Jamieson Hall, were examined for their prospects of reducing heat loss by replacing single-paned windows with double-paned ones. By doing this, Cornell University could save a lot of energy and reduce its carbon footprint. The goal of this project is to raise awareness of this widespread problem of energy waste all over the world. And in order to do this, we first need to go to the classroom.
Alright class, today we're going to be talking about windows. You guys like windows?
Yeah.
You shouldn't. Windows are evil. Today we're going to learn why windows are the cause of global warming. This is a schematic of a window. Here's the wall, and here's where more wall should be. But it's glass. For some reason people want to be able to see outside. Now the problem with having windows is there's heat transfer through them. Bad. This wastes energy, and well, it kind of makes your house uncomfortable too. The simple heat equation is given by terrible Q. Change in heat is equal to the mass times the specific heat capacity of the substance times the change in temperature. Now this works in chem lab, but it doesn't work when we're dealing with windows, so we're going to use a different equation. Much better equation in my opinion. Here we go. We're going to use this one, right? Here. Play it again, Mr. Coe. Alright, Q is of course the heat loss. And instead of this delta T value, we're going to be using heating degree days. Take a minute to explain that. Now, when you're dealing with some, massive water or something, delta T is fine. Fine. Need that eraser. I had a very big class today. It's something the oil companies came up with in the 18th century when they tried to figure out how often they'd have to deliver oil to their houses. They decided, or they found that this empirical formula, that if you take the average temperature for the day, subtract that from 65 degrees Fahrenheit, it's a reference state they found worked, and you sum this quantity up, over the entire year, that this gives you a good measure of how cold the climate is. And this will be dubbed the heating degree day. Alright, this value should be familiar to you. A, it's the area of a window. And this value U may not be as familiar to you. That is known as the thermal conductivity constant, and it's characteristic of all substances, but we only really care about it things like windows, because we don't really care about heat transfer through a desk or a human body. Alright, so this we can look up. In the Ithaca area, this value is around 7,000, which is pretty high. This we can look up as well. For a single pane window, use about 1.1. For a double pane window, it's about 0.7. A, we can't look up because it changes in every building you've got. So that's what we're going to need to find if we're going to calculate Q. So let's go find A. Alright, let's get some calculations. Q equals H T T plus sum U A. Alright, who's got the area calculations?
Not me.
Not me.
Does Harry have the area calculations? Where's Harry? Harry, you're waiting. John! Harry, would you kindly calculate Q for us?
Professor Nick, I'd love to. So let me get over here. Well, with the areas that I calculated, Donlin had a window area of 9,754.47 square feet, and Jameson had a nice window area of 7,174.51 square feet. Now, using our U values and our heat degree days, just plug it into the equation. As you can see here, Donlin has a heat loss through its windows of 1.855 billion BTUs per year. And Jameson, using its values, has the heat loss of 1.365 billion BTUs per year. Now this is with single pane windows of old construction. If we were to change this to, let's say, double pane windows, we could significantly reduce the amount of heat loss we get through these windows. As you can see, the values for the double pane windows, Donlin is at 1.197 billion BTUs per year, while Jameson's dropped down to 880 million BTUs per year. And the difference you can see is right here.
This is the Cornell coal plant. Much of the campus's heating comes from here. Coal power is known to be a significant contributor to CO2 levels in the atmosphere. Based on our theoretical differences in heat loss in Donlin and Jameson, and if we assume that coal emits 2 pounds of CO2 per kilowatt hour, then Cornell can reduce Jameson's carbon emissions by approximately 283,600 pounds and Donlin's by 385,600 pounds by simply switching from single pane windows to double pane ones. Imagine this for every old dorm in the entire nation.